Welcome to the Organic Chemistry Podcast. I'm Dr. Brian Lloyd, and this is my Scribblecast where we provide organic chemistry lectures and take up chemistry problems. In this case, we're doing an organic chemistry problem dealing with formal charge. In class, we produced an example of a Lewis structure in the special case scenario for H2SO4, sulfuric acid. The structure on the left is what we got with the Lewis structure solution when we followed the 8-electron rule for sulfuric acid. The one on the right is a special exception case Lewis structure which occurs because sulfur, being in the third role, has accessible empty 3d orbitals in which to place electrons. Because it's in the third role, sulfur can violate the octet rule and have more than 8 electrons. You were told that either structure would be accepted for the Lewis structure for sulfuric acid. Because of this, I wanted you to go away and calculate the formal charge for every non-hydrogen atom in both structures and then compare the structures and take a close look at them. So let's do that now. We're going to begin with the structure on the left. And because we have two different types of oxygens, that is, we have oxygens here which are attached to sulfur that have a hydrogen, and we have oxygens here attached to sulfur which have no hydrogen, we're going to label them differently. We're going to label the oxygens with the hydrogen oxygen alpha, and the oxygens without the hydrogen oxygen beta. And we're once again showing you the organic chemist's propensity to use Greek nomenclature, Greek letters. So over here, these will be oxygens alpha, and we'll use on the one on the right, the ones with the double bond will be oxygen beta. Okay, so what we're going to do now is carry out a formal charge calculation. Now, if you remember, formal charge assumes equal sharing of electrons and bonds. So when we look at an atom, we count up all the lone pairs for that atom, and then we split the electrons and the bonds down the middle, giving one to one atom and one to the other. Now in formal charge, you must first write down the total number of valence electrons, the valence electrons of the element. Oxygen is in the periodic table, the second row, and if you count from the left, you will determine that oxygen has 6 valence electrons. This is determined, this first number comes from the periodic table. Now let's do oxygen alpha if we can. I'll just label this. So this one will be oxygen alpha, and this one will be oxygen beta. So let's start with oxygen alpha. And oxygen alpha, like all oxygens, has 6 valence electrons. Let's count up how many electrons it has in the structure now. It has 1 lone pair, 2 lone pairs, that's 4, and it gets 1 electron from each bond, 5, 6. So 6 minus 6 equals 0. Now, you must remember to multiply this by 2. Why do we do that? We have to multiply it because there's 2 oxygens. So 2 times 0 is 0. Okay, so we're done. Oxygen beta. Oxygen has 6 valence electrons. And if we count up the lone pairs, we get 2, 4, 6. We get 1 for the bond because there's equal sharing. So 7. 6 minus 7 equals minus 1. And we have to again multiply this by 2 because there are 2 oxygen betas. So the total charge contributed, each oxygen that's beta has a minus 1 charge. So the total charge from the oxygens is minus 2. Now we can do the sulfur. Sulfur is right below oxygen in the periodic table, so it has 6 valence electrons. And we count up the lone pairs. Well, we see there's no lone pairs around this sulfur, but there are 4 bonds. Sulfur gets 1 electron from each of those bonds, so 6 minus 4 equals plus 2. There's only 1 sulfur, so we multiply sulfur, if you like, times 1. Plus 2. And now I can continue and do my net charge. Add it up. And you got to make sure the the total charge, equals what's given in the case of H2SO4. 0 plus minus 2 plus plus 2 equals 0. And when H2SO4 was given to you, it had no charge. So this works. It works well. We now can repeat all this for the structure on the right. And we can do so. We got formal charge of oxygen and formal charge of oxygen and formal charge of sulfur. And I'll just change pen color here for a moment. Oxygen alpha, oxygen beta. So we know which one we're working with. Okay, now oxygen alpha, this time it's exactly the same structure as the one on the left. The oxygen labeled alpha has 2 lone pairs, 2 bonds. 6 minus 6 equals 0. Oxygen beta is a different structure this time. We start with 6 valence electrons. The first number, again, is from the periodic table. And we see he has 2 lone pairs, so that's 2, 4. He has a double bond. He gets 1 electron from each bond of the double bond, so 2, 4, 5, 6. 6 minus 6, again, is 0. And sulfur, 6 valence electrons minus no lone pairs, so he gets 1 for each bond. 1, 2, 3, 4, 5, 6. 6 minus 6 equals 0. Now each of these oxygens is times 2. Well, that equals 0. And because there's just one sulfur, it's times 1. Again, that's 0. And so we had 0, 0, 0. Well, guess what? Net charge equals 0. Wow. Okay, so there we have it. We can actually write the charges we got. Let's use a different color for that. On the left-hand structure, sulfur was found to have a +2 charge. Oxygen -1, oxygen -1. In the right-hand structure, there is no charge. Now, I did say it doesn't matter what structure you come up with on the test. I will give you full marks as long as you get the formal charge correct. But one might want to ask the question, which structure is best for Lewis structures? Well, in actual fact, since you're told that third row elements can violate the octet rule, and since opposite charges attract, it is highly likely that the electrons will be dumped towards the sulfur to create the pi bond. And in fact, this better fits the experimental evidence that we have for sulfuric acid. However, having said that, we should note that some charge separation is reasonable based on electronegativity. Even with the structure on the right, because of electronegativity, we expect oxygen, which is more electronegative, to have delta minuses on them. And hence the sulfur would have a delta plus. It might not be a full +2. Nevertheless, having said that, I will accept either approach as a correct solution for the Lewis structure for sulfuric acid. Well, there you have it. Thank you very much.